So I took this doubling every year and extrapolated it 10 years from 1965.
All right, so it looks like we are not having a lot of you here today. So let's just go ahead and start. So today we are talking about Lab 4, right? So Lab 4, so previously in Lab 3, you already have the processor without branch support. So definitely, as you can imagine, being the step to the Lab 5, because because in Lab 5, all we want you to do is that given a single cycle processor, that's pipeline it. And in Lab 4, that what we are going to do is that we just want to lay out a foundation for you to pipeline the processor. So Lab 4 is actually a single cycle processor that should be working. For most of the instructions that we are going to have in a benchmark. So here's what we have in Lab 2. So Lab 2, you have the data paths, and Lab 3, you are adding the control paths to Lab 2. However, for Lab 3, the control path doesn't support branch instructions. So now look at Lab 4, right? So Lab 3 and Lab 4, they are not, well, the red part and the black part, they are not different. So the blue part is the addition that we need for Lab 4. So if you look at that, what we really need here is that the jump right now has to connect to a mux. And this mux getting two inputs. One is the branch target. So the branch target is calculated as the sign extended value of your branch instruction and shift it left by 2. And why are we shift it left by 2 is just because for every instruction in MIPS instruction set architecture is 4 byte wide, and 4 byte you only need 2 bit to encode their address. So to save, since every instruction, every PC's last 2 bits, they are 0. So we just, when we store the offset, we shift it right by 2 so that we can accommodate wider range of the offset. So right now we just shift it back in the circuit. And then if you are familiar with the standard of the MIPS instruction set architecture, you know the offset is actually calculated. The target PC is actually calculated by the current PC plus 4 plus the offset. So the PC plus 4 comes from this adder. So that's why we have this line. And then, well, maybe I should use a different color. Okay. And then for the other input, this one, please pay spatial attention to, because I don't think the document or the textbook make it crystal clear. So if you are familiar with, if you check the jump instruction in MIPS instruction set architecture, the target address of a jump is actually using the top 4 bits of the current PC plus the immediate field, or say the last 26 bits in the jump instruction shifted left by 2. So this is the value you should have as another input of the mux. So this part comes from the top 4 bits from your PC, and this must be done correctly, otherwise your processor won't be able to function correctly. So that's an important thing, right? And so using this, right, the jump signal would help us to tell if this is a jump instruction, because if it's a jump, then we take this one. If it's a branch, we take this one. However, to decide if we want to use jump or branch output, then it becomes that the LU, it output a branch or jump out signal. So if any of this is true, so that's why we have an OR gate here. If any of this is true, we are going to use the input from here to decide the next PC instead of PC plus 4. So that's this part of the logic. And with this part of the logic, so with this part of the logic, we are able to support jump and branch instruction. So that's the main addition we need to do in Lab 4. However, I do want to warn you, most of our students are struggling with this size in. So this is a new addition in Lab 4 is that, for right now in the class, we spend most of the time talking about load word. Load word is a 4-byte load instruction. However, there are instructions like load byte, which only load 1 byte of data. So if you want to get your load size correctly, you need to have a size in signal going into your data memory, tell you how many bytes that I want to load. And then your instruction must put that byte into the register accordingly. So that's the main thing that you need to do in Lab 4. So given that you have those elements, this is what we have previously. But now extending it, you will see, well, you need a size in signal. And in addition to load word, store word, we also have load byte, load half, store byte, store half. And half means like we have 2 bytes, right? So this and you can check this is the extended control unit. Another thing that you might feel interesting here is that there are 2 instructions, BLTZ and BGEZ. They share the same OP code, but you have to output the function in differently. So how do we tell this? So later on we will discuss that, but this part you have to take special care of. And this is another control unit, and that you need to extend. So this set of within this set of control unit, one thing I wanted to take special care of is that so in your assembly language, you will see there are no ops. So no ops, they are actually implemented using SLL. So so in my class, I like to use AND 000 or add 000. However, in MIPS, they are actually using shift left logic, and by using opcode 0, function code 0, function in 1111. But how do I know if this is doing a no op? It's just by if the destination is 0, then it's a no op. Otherwise, for the regular SLL, you should go to this line, which your function code should be 0, and your destination should be 1. So this is a special case of the SLL that we use. And how do you tell this is that you have to specifically check if the destination is 0. If it's 0, then this is what the corresponding function code that you have to set. Otherwise, your instruction is not going to function correctly. 2 instructions that are problematic, as I mentioned, for BGEZ and BLTZ. Their opcode are both 1. How do you tell? Is from their RT register. So for BGEZ, its RT register is 1, and for BLTZ, its RT register is 0. So right now, although we give you the very high-level schematics, however, there are a few instructions you have to take a look of their RT and RD. All right, so so these are the tips that you need. And also here are a few instructions like LUI, which load upper immediate, meaning that I am loading instructions immediate field to the upper part of the register value. And jump and return, jump and link, jump and link are, these are the instructions that we would use to do function calls. And their functionality are described here. So for jump and return, you just set your PC to return address. And and the return address is an input of is a register input. And jump and link, that's what we use to call the function. And the return address, so when you do this, you have to save your PC plus 4 to RA register. And the PC, the next PC, as we mentioned, right, it's PC plus 4, the upper 4 bits of PC plus 4 and your immediate field shift left by 2. And for jump and link register, you are making your you are storing your register you are storing your return address to another register. So that's the stuff. Okay. So modify this. So your task in lab 4 is that you have to modify the schematic to support all required instructions. Extend the control unit to support all the required instructions. Here's the benchmark, as we said. And well, when you support new features, you have to do a sanity check that you don't break the old thing. So that's why we still have the no branch hello world. And you will also have a hello world with branch. And because we have function calls, so we also wanted to support Fibonacci number. So this is the 3 benchmarks that you have to do. And for interviews, show us the schematics, show us the waveforms of the 3 benchmarks and the output until the end. Measure the instruction count, total cycles, CPI, and make a table, present it to us. And report the Fmax, meaning the maximum performance that you can achieve in your processor. All right, other than that, that 4 due next Friday, that 3 due this Friday before 5 p.m. But again, this interview, they are soft deadlines. We have this deadline just because we want to check that you guys are on track. Other than that, do you have any question? Okay, if not, then we will see you in the office hour or another lecture later. Have a great rest of the day.
Floating high into the darkness. I hope I get there soon. It's so many things.